Good morning. Today, this morning lecture and afternoon lecture, whatever that I'm going to complete, would complete till in module 3, central impact. That's non-central impact that we will see after our midterm test. So for your examination, midterm examination, you have first module. It's not very big module. It's short to give you an overview. And we had two periods for that. You can go through those first 3 lectures for that. And then module 2, we have looked at detail uh, different crash testing procedures, right from test environment preparation, vehicle preparation, what are the measurements and what are the critical observations that go in with your crash test. So we have looked at offset frontal impact crash test. We have looked at that is as per Federal Motor Vehicle Safety Standard 208. And then we have studied about side impact procedure recommended by FMVSS 214. And we have looked at those all testing procedures every stage by stage, like vehicle preparation, test environment, measurement, observation. So in these 4 headings, we have looked at that in detail. And then we have also in module 2 learned about rollover stability. So simple, looking at thumb rule of threshold lateral acceleration given by T by 2h, where T is tread of your vehicle or track width, or 2h is h is referring to CG height from the ground. So that gives you a threshold acceleration. At that point, there will be initiation of your rollover, is what we have seen. So when you say rollover test, it is basically happens because of unstable state of your vehicle. So that can happen not necessarily only like heavy vehicles. So you see most of the cases, one of the video we have seen, SUV can get rollover problem when even the smallest gentle offset impact, right? So that happens. So this rollover stability or rollover vehicle model to do what currently we are looking at learning in module 3, central impact is not sufficient. So that is where you require to go in for understanding what do you mean by non-central impact or eccentric impact. So that portion I would cover in our course after your midterm test. So currently, after learning many test procedures and many crash videos to understand, no, we have marched into module 3. In module 3, essentially, it is studying about collision models. So in collision models, when you say how these fundamental mechanics principles are employed in creating such models. So we are going to look at simple handleable in the classroom, like solving problem models only in our course. And you will also have some of the literatures wherein you see how that is extended to carry out in full-fledged vehicle finite element model or lumped mass spring model. Research vehicle models are used in OEMs in product development center. So our module 3 now is to revisit our fundamentals and try to look at closed form solutions or formulas for quantifying accident severity, right? Crash severity. So that is what is essentially the crux of this module 3 that we are going to learn, and we are already spent some 2 periods for that. And today morning lecture now and then afternoon lecture I would complete central impact. So far in central impact, we have looked at direct central impact and oblique central impact uh, formulas or the physical phenomena, how it has been explained. So what essentially you have done is you have applied Newton's second law in its other form called linear momentum conservation form, or it can be of essentially what is it, impulse and momentum principle or work and energy principle. So these are the principles from fundamental mechanics are describing collision phenomena, right? That's what we have learned so far. And I'm going to explain you today a simple collision experiment, and that would help us to have some systematic understanding of energy loss to calculate, right? It is simple, but we have to have some ready formula, so that it is easy, that you would be able to quickly make an assessment of your crash event. So that's what is the idea. And the reference for today, whatever I'm teaching, is again from Matthew Hume, from Vehicle Crashworthiness, our textbook, chapter number 7, right? Yeah. So with that, for you, now let's get into our lecture. Let me just share my screen. Just a minute. So let me share my Act Inspire board. So I hope you are able to see this board. And today's lecture number 12, and today's date 21/7/2021. So I'm going to explain you today, importantly, a simple collision experiment. Again, we will revisit the same application of this impulse and momentum principle and work and energy principle. But we are going to derive an expression for a closed form formula, that in one formula we would be able to say with the vehicle details what are the energy loss, percentage energy loss. So this is what is I'm going to explain you now in this particular period. And to understand that, I'm just going to use during this derivation many of my keywords. So I just write down the keywords on the slide so that you would be familiar with them. That would facilitate you to understand the whole class of today, right? So the keywords of today's class are effective mass, closing velocity. So whatever that I am writing down, you should be able to explain what is it to this subject, right, of today's class. And then you should understand what is total crush energy, total crush energy. Then, of course, we have looked at deformation phase, restitution phase, and let's look at the energy absorbed. And energy absorbed, rebound energy. And we will see what is energy dissipation. Energy dissipation, or that's what is called final energy loss. Final energy loss. So these are all something that no, we are going to harp upon, so that we will be able to predict something what is called crash severity. So these are the key words that you should always be aware of and knowing what it is all. So what does this effective mass? So effective mass is the two vehicles are colliding, vehicle to vehicle collision. Both the vehicle mass is there, you would be able to come out with an effective mass where you are able to say what would be the total energy loss from that. So that is the idea. What is closing velocity? So closing velocity is what is the velocity of approach, relative velocity of approach just before collision. So like that, we should be very much familiar with this all keywords or words that I have written now on this all the time, so that you are able to go. That's why you see any research article you are reading, you see an abstract. So that paragraph when you read, you know what is these researchers are doing it all about in short. If you feel that is relevant and provoke you to go through further, only you will start reading the paper. So that's why abstract has to bring in a clear-cut idea or objective what the researchers intended for the research, and what are the methodology they apply, and then what are the results and the interpretation, or there are recommendation. Like these all are brought in paragraph is what we call it as an essence or an abstract. And after that, you see there are keywords. The keywords are familiar and you understand those definitions, and that would facilitate the reader to go through the paper comfortably and get all. So I felt my today's lecture, if I start with telling you what all an important keywords that if you understand, and you would be able to define what is this crash reality, right? What is this final energy loss calculated, so and so on. So if this is all the idea, I'm going to now proceed with explaining you the simple experiment. So what is that very important? So far we have looked at in this particular impact models, application of impulse and momentum principle and work and energy principle. And you see that these events not only involve the impact and excitation exchanges, but also there are energy absorption and losses. That's what is very important when you have to talk on vehicle crashworthiness point of view, right? So if we are able to understand this total crush energy, energy dissipated, or energy that's called final energy loss, you would able to define what is crash reality. So that's the idea. And this can be well done by two basic approaches. One is called relative velocity approach. Another one is called fixed frame reference approach. So we will do them in subsequent class. And now I'm going to explain you a simple collision experiment. Simple collision experiment. So the word simple collision experiment says that it's got a simple pendulum, right? And that we call it as a stationary fishing bob pendulum, right? A simple pendulum. We call that as a fishing bob, stationary. This is called fishing stationary bob, right? So you know the simple pendulum could have been looked at in your clock, and that is oscillating and so on. So simple pendulum oscillation is the best example to understand an important motion called the simple harmonic motion, right? That's where we could define your governing equation by Newton's law and so on. We know about the motion of simple pendulum, and this mass, this bob mass, let us call capital M, right? And then this bob is now stationary, so there is no velocity. This is state zero, let's say, event zero. So next event, this is going to be hit by another ping pong ball. So what is ping pong ball? That is coming from a toy gun. So I have a toy gun, and that gun shoots this ping pong ball, and that comes and going to hit this. So let's call that as this small mass, small m. So what is this? It is ping pong ball exit from a gun, toy gun. Right? So this comes. So this comes with what? With the velocity. So let me call that velocity as v, small v subscript m. Small m is the small ball mass. Capital M is the bob mass. And the mass, if you look at, m is greater than small m. Right? M is greater than small m. This is bigger mass. And here, what is the velocity at this state position 0? The velocity of this, let me call capital V and subscript capital M. And that velocity is 0. It's not hit. So it comes and it is going to hit this bob. And then we are going to look at now what would be its second state. So at the time of hit, and just after the hit by this, I will have the ball and the bob, and their velocities just after the hit would be small v dash. Anything in this subject with the prime if you put, that is after collision. And this would be capital V dash capital M. So this is what we call it as separation velocity. So approach velocity is only the velocity of the ball as it is stationary, and after the collision, separation velocities are Vm dash and Vm. So what would happen? It will go to second event. So this will make a hit and this will be oscillating after that. This will fall and this will be oscillating. That's the motion impended onto this bob that we know. So let me look at now the second state of our observation after the collision. So the collision is only at this point now. After the collision, what does that is going to happen? This bob is going to displace. Is going to be displaced. Is going to be displaced, and the displacement to understand, let's call this length L and this angle alpha degrees, right? And from its original somewhere here it was there, that has gone to this position. So the mass center has been displaced now by a height h. Of course, this ball hits and then it goes, and then you have this ball motion here. It is also there, right? This velocity it hits, then this is the velocity v m dash, and this is that it has gone there, and this is the point where it is going to return its motion. So this is its maximum displaced position. So now I describe this experiment by event 0, 1, event 1, 2. Like that we are describing. So this impact the smallest duration, right? So now what is the idea of this experiment is to get a closed form formula for the muzzle velocity. So this muzzle velocity is nothing but velocity of the ball. With which it hits the bob, right? So this velocity I had to find out, and also I had to find out an energy loss during this. So you can consider there is no energy loss because of this event 0 to 1 and 1 to 2. Energy can be completely conserved, you can consider. But it is restricting reality. In reality, there are energy loss because of the collision of these two, ball and the ball. That has to be accounted. If you account that, the velocity what you get and the energy loss is different. If you do not account, the impact velocity Vm, small vm would be smaller. So you make a mistake. So we will see that at the end. But let us now proceed to derive a closed form equation. So derive closed form formula for this, right? So how are we going to proceed? So let us go ahead with this. As we have defined in the picture, Vm is the initial velocity of ball, Vm dash and V capital M dash, separation velocities of small n and capital M respectively. So now I am going to take event 1, 2 first. Event 1, 2. So between event 1, 2, if I apply what conservation of energy, I am going to look at only the bob motion. So if I look at the bob motion, so before event 1 at initially bob was stationary, and once that is hit by ball and that is under motion, and that motion is going to reverse at its maximum angular displacement, right, with respect to point of oscillation. So we are looking at from 1 to 2 that. So 1 is what is this point? 1 is this point. This is 1 point and this is position 2. So between 1 to 2, I'm going to apply my energy. So at point 1, it is going to have maximum energy, kinetic energy. At point 2, it is point of reversal. So velocity at that point is 0. So it will have potential energy. So I would be able to write my equation of into capital M, it's mass of the bob, into V capital M dash. Look at this dash square. So this is what is equal to capital M G into H. So where this H can be from the geometry of the setup, found out that total length minus this angle here is L cos theta. So L cos theta, right? So you understand this. How does it come? Simple. So this is point of inch and this is your bob, this length L, and this goes here, position 2. So this height H can be obtained by, this is L, so this length is L cos alpha. L cos alpha, if this angle is alpha. So L minus L cos alpha. So L, if I take it at 1 minus cos alpha. So that's what is H. So from this, I can find out what is this velocity that's given by under root of 2gh. That's simple. So that's equation number 1. So I get my velocity, what is that is imported onto the bob by the ball. And that is given by the observation of what would be its displacement maximum given by this angle alpha. So I would know as the bob hits, as the ball hits the bob, what is the energy that is imparted onto it at that point of time. So in this picture, as it hits, we have this velocity Vm dash. So what is this velocity? Is what is given by simply under root of 2gh. That's very well known and you know, but take that. Now, let us take event 0, 1. And that event 0, 1, let's apply conservation of momentum and what we have learned earlier, the definition of coefficient of restitution. So using these two, I would be able to get. So here, what am I going to do? Apply conservation of momentum and the definition of coefficient of restitution. So applying these between this event, I would be able to write now what is my initial momentum just before the hit. It is mass of the ball and velocity of the ball. And that would be equal to what at the start of the uh, 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 deformation phase. That would go with this, and then the momentum of two entities. One is after the separation that just finishes the collision. What are the momentum conserved? That would be small m v small m dash plus capital M capital V substrate m dash. So this is my equation 2. So this equation is consideration of linear momentum equation. So why capital M Vm is not there, as Vm is 0, right? So you may here Vm is 0. Vm is 0. That's why it is not there on left hand side. So this is the equation number 2. Now what is the equation definition of E? Definition of E is relative velocity of separation by relative velocity of approach. So if I write that expression what we derived in the previous class, so small m dash minus capital V capital M dash. This is after collision, just after collision, divided by capital V M minus small v m. And as this is 0, this goes off and you get this, and that would be your equation 3 here in this case. So now look at this equation 2. I'm going to rewrite this equation 2 for convenient to have a simplified formula. So I'm going to divide this equation 2 by small m and small vm. And if I do so, I would get this equation 2 as 1 on one side, left hand side, that's equal to a small m goes, so small vm dash by small vm. So velocity of ball after collision divided by velocity of ball before collision, just before collision, right? And that's going to be here plus capital M by small m into V capital M dash by Vm. So now this capital M by small m, I'm going to replace by a letter Rm. The ratio of this mass m by m. So if I do so, I'll get my equation here 1 plus Vm dash by Vm plus Rm Vm dash by Vm, right? So now what shall we do further is this. So this equation 3, I'm going to rewrite for a convenient form. So I'm going to retain, see this is going to be divided, this Vm is 0 here, so this is going to be Vm dash by Vm, that's with the minus sign, so minus Vm dash by Vm, and then it's become plus capital Vm dash by small Vm, that's equal to E. Equation 3 is written again like this. And from this, I'm going to write for the expression of this expression I needed. So what is that going to be? Capital Vm dash by. So ultimately, we have to remove this explicit appearance of velocities and to write in a formula in terms of Rm and E. That's the idea. So we just do this manipulation. So Vm dash by Vm is going to be equal to E plus V small m dash by V small m, right? So this I am going to put. Why do I write this? I want to eliminate this Vm by Vm. So I will put this in equation above equation. So put this into this equation, and that becomes what now going to be. Let's rewrite this. That's going to be now 1 minus, right? here this is equal sign. Sorry, this is equal sign. Right? Yeah. So now this is going to be like this. 1 equals VM dash. So I'm replacing this with this. So I'll rewrite and then again go ahead. So small VM dash by small VM plus RM. In this place, I'm going to replace it by this into E plus V small m dash by VM. So now again you see I can do this. So Rm E I'm taking on one side. So 1 minus Rm E. So left hand side without velocity terms I have. On the right hand side I'm going to have now this Vm dash by Vm. If I take that out, V small m dash by Vm, I will have what 1. And this term is already taken on left hand side, so this term will be there. So that's going to be Rm into this. So that is taken out. So this plus Rm, right? This plus Rm. So now I can easily eliminate this velocities again by substituting here the term. I have already got it. So this has to be again eliminated, right? So how do I do that? I wanted to have this expression now. So it's not eliminating. I wanted to have the ratio of ball velocities after and before collision. So that would be now simply obtained in terms of V and this mass ratio. So small Vm dash by capital Vm is going to be 1 minus Rme by 1 plus Rm. So if I know two colliding vehicles, their masses and the coefficient of restitution, then I would have these ratios. Or if I know, if I know Vm dash I do not know, E also I do not know. At least I'll have an equation relating Vm dash and V. So that is all readily available. So this is equation 4. A. We can also express similarly V capital M dash by Vm by substituting this into this in terms of Rm and D. So I'm going to do this now for this term as well. So what is this term? V capital M dash by V small m, V small m, and that's going to be now E plus this. So I'm going to replace this over here. So it is going to be E plus this term here, whatever is there, now will be replaced by this 4a, equation 4a. So that's going to be 1 minus Rme by 1 plus Rm. So I can rewrite now this taking LCM on both sides. So it's going to be 1 plus Rm E plus Rm plus 1 minus Rm. So this terms goes off. So it's going to be 1 plus G divided by 1 plus Rm. This is equation 4b. This is equation 4b. So if I have to get the velocity of Vm dash, that is your bob velocity, and that is given by equation 1 under root of 2gh. And we can get, we know that initial velocity that is triggered and coming exit from the toy is small Vm. So this ratio is given by 1 plus E by 1 plus Rm, where small capital Rm is referring to mass ratio. So these equations are quite useful equations. Now, continuing with that, what is our idea is to get energy loss, is to write an expression for energy loss and muscle velocity. So now the initial velocity of the mass m is equal to what? From this I can find out, right? That would be Vm, initial velocity Vm. That's what we are interested in. And that would become now in terms of this Vm dash into 1 plus Rm by 1 plus E. And I can again rewrite this as 1 plus Rm, yeah, Rm by 1 plus G into root of 2gh, because capital Vm dash is root of 2gh. So this is equation 5. This is equation number 5. Right? You have any doubts in the process of doing, please ask me. Otherwise, let me proceed again. So now let percentage of energy loss, that's what we are next interested in. But that, what is the formula to get? How do you get that percentage of energy losses? Energy loss by initial kinetic energy. So energy loss by initial kinetic energy. So energy loss is what? Initial kinetic energy minus final kinetic energy by initial kinetic energy into 100%, into 100. So I would get here for this that following. So let's call now this is going to be 1 minus E kinetic energy final by kinetic energy initial into 100. That's equation number 6. So this is percentage energy loss. This percentage energy loss again I have to express through Rm E. So I have my parameters E, masses. So I have to get everything in terms of Rm and E. That's an idea. So for that now let me substitute these expressions here and proceed to derive. So what is my initial kinetic energy of the system? It is only due to the ball mass. So half into m into v small v m square. Only this. And what is my final kinetic energy of the system? What are the velocities of both the particles after collision? So there are two velocities immediately after the collision. One is by Ball velocity, so that is half m, that offers this kinetic energy, half m small v m dash square. Another one is the Bob velocity, so half capital M capital V dash capital square. So this is what is final kinetic energy. So let's write this as equation 7. So now knowing these two, now I can substitute them into equation 7 and find out the expression. So let us proceed further. So I would get now percentage energy loss, that is going to be equal to kinetic energy initial minus this. So it is 1 minus this. So it's 1 minus kinetic energy final is half m v m dash square plus half capital M v capital M dash square minus half m v small m square divided by initial kinetic energy half small m Vm square. So this is substituted in equation 7, equation 6, in equation 6 substituted into this all into 100%, right? In terms of to get percent. So let us put at the end the percent. So energy loss is this. So let me just work out now for modifying this. Now how will I do that? See, let's divide. Let's divide now. So energy losses, this is not 1 minus. So energy losses this now. When I divide this first term and this term, you see half m that goes off, and it's going to be yeah, am I doing correct? Yeah. initial kinetic energy minus final. It is initial kinetic energy minus, I'm sorry, this is initial kinetic energy minus final kinetic energy. So please rewrite this. Sorry, let's rewrite this all once again. Initial kinetic energy is half mvm square minus half small m vm dash square minus half capital M capital V capital M subscript dash square divided by half m small v m square. So this is the expression. So this is going to be 1 minus. So this is going to be Vm dash square by Vm. And when I divide with the third term, it's going to be 1 half goes m by m is become Rm. And V capital M dash square by small Vm dash. Sorry, small Vm square. So this is their expression. So now I can substitute because I have already the equations for Vm dash by Vm square, Vm dash by Vm and capital Vm dash by small Vm. I have this expression. So if I substitute them here, 1 minus, that's going to be 1 minus Rmv, since it's square, divided by, what is Vm squared? 1 plus Rm. This ratio is, what is this? We have already derived. This also becomes square. So this is for this first term. In the second term, it is going to be Rm into, we have also expressed this by 4b, and that is going to be 1 plus E square by 1 plus Rm whole square, right? And then now let me just do rearranging. I can also give you as a work. Anyhow, let us do it here now. Let me take this LCM 1 plus Rm square, and it's going to be 1 plus Rm. So I'm expanding that terms, right? The 1 plus Rm square is going to be what? 1 square plus Rm square plus 2 Rm into 1. So 1 into this is this minus 1 plus again this 1 minus so this is a minus b whole squared. If I expand that, 1 squared, so minus minus 2 Rm e, that the minus of minus become plus, so 2 Rm e and plus Rm squared e squared. So minus when it goes, it is Rm square e square. And similarly here it is minus Rm into this. So it is going to be Rm into 1. So that's Rm. And e squared. So that's going to be minus Rm e square. And then 2e into Rm. So that's going to be minus 2e Rm. This you can see, these terms are cancelled. These two are cancelled. And the remainings are there as it is. Is there any term 2Rm and minus Rm? So it's become Rm. So now I'm going to couple this terms together so that it's convenient to rewrite like this. So this is equal to, now in denominator, same 1 plus Rm square, I'm having it. In numerator, I'm going to take this term, Rm squared, and I'm going to take this term, Rm squared term. So Rm, if I take out, in that Rm square, if I take out, what is that? I get 1 minus E square. So these two terms are first used. Then plus, I'm going to take the remaining rest of the term. So it's what are those terms? You look at here, this 1 is there and this 1 is minus 1. That is also cancelled. So 2Rm minus Rm, that's going to be Rm minus Rm into E square. So Rm coefficient, I'm retaining and taking it out. So that Rm, when it is taken out, it's going to be 1 minus E square. So see here 1 minus E square, here 1 minus E square. If I take that out, I'll get Rm squared plus Rm. That Rm, if I take out 1 plus Rm into 1 minus E square by 1 plus Rm square. So here again, this Rm and this square goes off. So I would be ending with a simplified expression in terms of Rm and E, the total energy loss. So that's going to be Rm into 1 minus E square by 1 plus Rm. Is what is the energy loss. So percentage energy loss, if I say, it's going to be Rm into 1 minus E square by 1 plus Rm into into 100%. So this is that expression, and let's call this equation as equation number 8. Right. So we can have here two important specific cases. Right. So you may think that it's a simple pendulum problem. So how can this be a collision experiment? Because it's hit, there is an impact, and that is what we are looking at. And here, these two special cases are going to help us whether that is this experiment can be equivalent to that of an impact test or not. So what does it depends on? That depends upon Rm value, m by m. So you can have the small mass very no smaller than very smaller than this capital mass. You can have this scenario. So if we take this scenario, what would happen to Rm? This is case 1. What will happen to Rm? Rm is very small, that ball which hits that huge mass of ball. If I assume like that, it's going to be an impact problem, right? So Rm is going to be almost equal to infinity because it's going smaller and smaller than this, and you'll have an infinite value, so infinity value. So this general problem then degenerate into vehicle to rigid barrier impact. So if this condition arises, for this condition, it is what is the general problem what we looked at now is reduces to vehicle to rigid barrier, impact problem. So that is what is this. It appears simple, but it can take a very huge complex impact phenomena. At that time, what would be the percentage energy loss? So if this is a scenario, what would be your percentage energy loss? Look at here. If Rm is infinity here, what would be the percentage energy loss? So for that, to see again, I'm going to rewrite this equation 8 also in convenient form to look at it. So if I substitute in this Rm equals capital M by small m. So this 8th equation can be, let me call this the 8A, and 8B equation would become percentage energy loss will be equal to capital M by small m plus capital M into 1 minus E square into 100. That is say 8B equation. So look at here now, if Rm is infinity, then this entire term is going to be what? It's going to be, here it's going to be capital M by capital M. Small m is negligible. So it's going to be 1. If it is going to be 1, my percentage energy loss is 1 minus E square into 100%. That's all. 1 minus E square into 100%. So it is not that we'll look at E value varies between 1 to 0. E value varies between 1 to 0 is with respect to the definition of coefficient of restitution. It cannot be greater than 1. It can be 1 for perfectly elastic impact. It can be 0 for perfectly plastic impact. So we wanted E value is closer to this perfectly plastic impact. So if that is 0 here, what is the answer? Energy loss is 100%. So energy loss is 100% that goes in deformation phase of your crash event, accounted by structural deformation and absorbed by the structure, vehicle structure, and the rebound energy is 0. So it is a perfect plastic impact, and the energy that goes into occupant is very less, right? So that is the case. So if the simple experiment that we have understood now and derived the expressions for the impact velocity of the ball and the energy loss in terms of masses and coefficient of restitution, that helps us to categorize this general problem into two cases. The case one is vehicle to rigid barrier impact. So I would be able to have this. So if I have my E value, I substitute here accordingly, I would be able to get what would be the energy loss, right? Or on the other hand, case two, if small m is much greater than capital M. So I have a huge mass and I'm striking the ball. The ball mass is huge, and if I strike, what would happen? Then what is this Rm value going to be? Rm value is capital M by small m. So if it is capital M by small m is down in denominator. This becomes huge and huge at one point of time. That's fraction, and it is almost can be equal to 0 at one point. So when it is 0 at one point, what would happen? Look at here. What would be my percentage energy loss if Rm is 0? Rm approaches 0, percentage energy loss is going to be, we had an expression here, this Rm into 1 minus E squared by this. So when Rm is approaching 0, the entire thing is 0. So percentage energy loss is 0%. So when it is the energy loss is 0%, that dictates E would be 1. Either E would be 1 or the impact vehicle are like this. So if a colliding vehicle is so huge on a small vehicle, it is there is no problem for the bigger vehicle. There is no energy loss for it. But other vehicle is, of course, no damaged thoroughly. But in this scenario, as far as this experiment is concerned, the general problem cannot be considered to be a vehicle barrier impact test. Instead, it becomes a simple pendulum problem, right? So the general problem becomes a simple pendulum problem. So general problem of this experiment becomes simple pendulum problem. Simple pendulum problem. So these are the two cases that we understand. So what is an important point here at this ending the lecture is, let's look at now a simple data for this. If length of this experiment pendulum is say 30 centimeters, and the angle alpha that goes is say 30 degrees. So can you find out what is small Vm and percentage energy loss? That's a question. So I leave it to you to answer this. Also, in case if you if we apply conservation of energy before and after impact, what is the velocity, initial velocity and energy loss. So when I say energy loss, you would immediately say it's zero. Why? We are applying conservation of energy. So energy is not conserved is very clear. That is what we calculated an expression for energy loss. So when you make an assumption, ideology that energy is conserved in such kind of collision scenarios, that is wrong. In oblique central impact, we have seen energy is not conserved. It's conserved is only in the plane of impact, because along the line of impact, momentum is conserved, but there is an energy loss, and that we defined E. That is very well understood. Whereas along the tangential direction, plane of impact, he had velocity before impact component of a vehicle is same as after the impact. So partially energy conserved, but not entire energy conserved. So that clarity is important. So in the same problem now, the simple experiment, if the length of this simple pendulum, the string is 30 centimeter till the center of the mass, and the angular displacement is 30 degrees at point 2, even 2, correct, point 2, then find out what is the velocity Vm and the percentage energy loss. In case you are forgetting, you are overlooking that the energy loss during impact you don't consider, and if you consider energy is conserved, you calculate what would be the energy, what is the velocity of impact, and then you see that cannot be counted. So these are the homework task for you, and I will end this lecture at this point of time, right? And we will continue with this in the afternoon, and we will understand what is this Kelvin's theorem. Correct. Again, that is all what is a fundamental only, but specific to looking at crash modeling, these equations are dealt, and these whatever I'm teaching is available in your textbook, Matthew Home Vehicle Crashworthiness, chapter number 7. Right. So with that note, let me stop today's class. In case you have a doubt, I'm happy to answer, and we will end. Any doubts?
No, sir.
No. Okay. So let me just stop recording.